Well, hello again. What I wanted to do was, for fluid mechanics review for exam 3. Right now, this is, for us, this is chapters 8 and 11. This is major and minor losses and drag forces. Okay, it'll be 3 problems. Okay, it'll be 3 problems. You will have what we call the timed questions, just like we did for exam 2, where you'll have 5 minutes to answer fundamental questions. Alright, so for each problem, I'm going to ask you some fundamental questions about that problem, how you're going to set it up, how you're going to approach it, what equations, what laws, what principles you're going to use. So, it's very similar to what we saw in exam 2. Then we're going to have the, there's going to be another assignment or quiz called the questions, okay? And then what I want you to do is I want you to, and there's going to be very clear, a lot of detail in the instructions for the exam, okay? And the only thing that's going to be different is I want you to load your PDF to the exam 3 assignment. Okay. So right now there's an exam 3 assignment area there within Canvas that you can go look at right now. On the day of the exam, which will be, of course, that's Monday, and whatever Monday is that? I think it's like May something. Whatever Monday, May calendar. I don't remember things that I can look up quickly, I always say. Monday, May 4th. That's when the exam's going to be. Okay? So Monday, May 4th. That's when your exam will be. You can go right now and find the exam 3 assignment area. Right, that's available, and I will convert it to where you can upload PDFs to it. There will be a questions area just like where you loaded your PDF to last time. The difference will be is this one is not going to have a place to upload your files. I want you to upload your files here because here I can grade them. I'm not going to have to print them out, grade them, scan them back in, and load them back as a PDF. Again, you get a copy of a copy of a copy. No, I can actually write, if you load them to this folder, I can actually within Canvas grade within Canvas. I don't have to print it, grade it, and then load it back. So if you'll load it, so I know it's an extra step and I apologize, but if you'll load your exam 3 questions, your solutions back to this exam 3 assignment folder that's available right now. And again, I'll make it pretty clear, give you some links. You're going to have 2 hours, must be uploaded within 2 hours of starting the timed questions. Alright, so don't look at the timed questions. Take a big long break, answer the questions at your leisure, and then several hours later come back and upload to exam 3 your solutions. No, As soon as you open a timed question, you need to write down when, write down when you start your first timed question. Write down, know exactly when you started your first time question. You have 2 hours from the time you start a time question to submit a PDF to the Exam 3 assignment folder. Right? Longer than 2 hours will lose points. And that way there's not, and if you have run into technical difficulties, you get it into me at 2.5 hours, you're going to lose some points. You're not going to be happy with it, but you can still get it submitted. So that way it doesn't lock you out. I don't have to worry about, well, how much time did you have between the time you were locked out and you actually uploaded the file? No, none of that. There's no timer built into Canvas on getting your PDF to me. I'm going to do that manually. So as soon as you open one of these time questions, it gets time stamped. You've got 2 hours from this point to get your PDF into the Exam 3 assignment folder. Canvas will not keep track of that time. You need to. Now, Canvas will keep track of these 5 minutes. After 5 minutes, I don't think it's going to let you answer these questions or submit these time questions. It's going to automatically submit whatever you've got on the screen. So work these quickly. That's the point. You need to be able to identify very quickly what type of problem you're dealing with and have some idea how you're going to set it up. That's the whole point of these. If you've done the homework correctly, you haven't just copied stuff from an online resource, you've actually thought about how do you solve these problems, you'll be able to answer these quickly. Okay? And then actually give me an in-depth, complete solution. That takes time, and that's why I'm giving you up to 2 hours, which is more than I normally give a class. I'm giving you up to 2 hours to get complete solutions, get them scanned, get them PDF, and send me the PDF. Okay? If you have any questions, send me an email. I'll be happy to get you pointed in the right direction. It's going to look very much like Exam 2. The only difference between this and Exam 2, aside from the questions and the content, is where you load your PDF, and that's in the Exam 3 assignment folder, because then I can grade it within Canvas. It's going to make it better for both of us in terms of the grading and the feedback. Okay? That's the reason I'm going to ask you to do that. Otherwise, logistically, it'll look very much like Exam 2 did. Okay? Content-wise, that's new. Well, actually not that new. I mean, in Exam 2, we talked about conservation of energy. And that's still really what we're dealing with in Chapter 8 is the idea of the conservation of energy principle, where we say P1 over rho plus V1 squared over 2. There's an alpha here, alpha 1, V1 squared over 2 plus GZ1. So all of the Bernoulli terms, essentially, the Bernoulli energies, the baric, the kinetic, and the potential energy, plus any input from a pump or a fan or a compressor. That's going to equal any work coming out of a turbine or any other device that's going to extract mechanical work, plus the baric pressure or baric energy out, P2 over rho, plus the kinetic energy out, V2 squared over 2, plus the potential energy out, GZ2, plus the energy loss. So this is Exam 2 stuff. This is pretty straightforward. What we're doing now is we're saying, look, the energy loss for completely filled conduits. All right, so if I've got a completely filled conduit, the energy loss is going to equal F, Darcy friction factor, times L over D, times V squared over 2, plus the sum of all the minor loss coefficients times V squared over 2. And this is the speed of, the average speed of the fluid flowing through the pipe or through all of the components, the bends, the elbows, the contractions, the average speed flowing through whatever's causing the loss. Okay? So, That is the loss term. Now, now again, for multiple diameters, right? If I have multiple diameters, this is a little more complicated. That energy loss is equal to the sum of all the Darcy friction factors for each individual section of pipe and multiply by its length divided by its diameter. So for every diameter of pipe or conduit, I'm going to have a different average speed within that conduit. I'm also going to have a different length and a different Darcy friction factor for every individual section of conduit that has a different diameter. All these terms are going to be different. If I have a single diameter, though, this simplifies. It's going to be the same speed, and therefore the same Reynolds number, and therefore the same Darcy friction factor, as long as it's the same speed, or the same Reynolds number, and the same type of pipe. But if it's a different kind of pipe, or it's a different diameter, every segment, every different area is going to have a different one of these quantities. And you're going to add all the minor loss coefficients through each different speed. Every average speed, or average velocity, every one of those is going to have its own set of minor loss coefficients that you're going to have to add all those up. So if I've got multiple diameters, an actual realistic piping system, this is what I need to do. For every different segment, I need to calculate the major and minor losses. Okay? But if I have a single diameter and the same pipe throughout, it's just major loss, minor loss, total length of pipe, Darcy friction factor throughout. Okay? Again, this Darcy friction factor, what we call the Darcy friction factor, that is going to be a function of the two dimensionless quantities, the Reynolds number and the relative roughness, epsilon over d. Okay? And what we did is we said, well, there's a couple of options. If we have what we call laminar flow, how do we know if it's laminar flow? That means the Reynolds number less than about 2300 for completely filled conduits. Again, where Reynolds number is rho VD over mu or VD over nu. Right, so there's two different kinds of viscosities. Either one of these, this mu over rho is nu, so either one works. If I've got a Reynolds number for my flow less than 2300, that means there's a very good chance all those molecules are moving in nice, parallel, laminar fashion. If that's the case, the Darcy friction factor just ends up being a constant value divided by the Reynolds number, and K is equal to 64 for circular pipes. There's a table in your text for other shapes of pipes, but if it's circular, it's just 64. Other shapes, it's going to be a function of the geometry. Okay? Alright, so that's if it's laminar flowed, and this is pretty simple. Okay, 64 over Reynolds number. If it's not laminar, okay, so if we have turbulent, yuck. If we have turbulent, how do we know if it's turbulent? Well, for sure, if the Reynolds number is greater than about 4,000, we're going to assume it's turbulent. Now, what do you do if it's in between? Well, we kind of need to see the flow, honestly, to be realistic. What I would suggest, because we can't just go look at the piping system in front of us, if you found yourself through a guess and check in between, I would just assume turbulent and move from there. All right, so we'll pick up on the next video from there. Loud pop.